Ethers and Epoxides, Thiols and Sulfides, Chapter 13. Objectives: 1. Properties of ethers. 2. Nomenclature of ethers and epoxides. 3. Synthesis of ethers and epoxides. 4. Reactions of ethers and epoxides. 5. Sulfides and thiols. 6. Syntheses overview. Your goals. By the end of the chapter, you should be able to name and draw ethers, epoxides, sulfides, and thiols, understand their properties, know the preparation and key reactions, apply synthesis and retrosynthesis. 1. Properties of ethers. An ether group includes an oxygen atom that is bonded to two alkyl groups or two R groups. Ether is a common functional group in many natural and synthetic compounds. For example, vitamin E has an ether functional group. Note that the R group can be alkyl, aryl, or vinyl groups, but not acyl groups. Acyl groups means we have a C double bond O. Consider the following. It is an ester and not an ether because we have O that is attached to an R group here, but this is not an R group, this is an acyl group. Ether structure. The bond angles in ethers is very similar to that found in water and in alcohols, with slight deviations. The oxygen atom is sp3 hybridized. The larger the R group, the wider the bond angle will be. In mixtures, ethers can only act as H bond acceptors. So if we have a mixture where one species maybe is an alcohol, then the ether would be able to accept an H for H bonding through its O. Recall, alcohols have relatively high boiling points due to H bonding. Ethers cannot H bond among themselves, and so their boiling points are much lower than alcohols of comparable size, but higher than similar sized hydrocarbons. Ethanol has a boiling point of 78 degrees Celsius, propane of -42 degrees Celsius, dimethyl ether -25 degrees Celsius. The larger the ether, the higher the boiling point due to dispersion forces. Dimethyl ether -25 degrees Celsius is its boiling point, but dipropyl ether 91 degrees Celsius. Use as a solvent. Ethers are common solvents used for organic reactions. They're used for organic reactions because they have relatively low boiling points, which means they're easily removed by evaporation, and they're fairly unreactive or inert. For example, diethyl ether, tetrahydrofuran, and 1,4-dioxane are commonly used to carry out reactions that are organic and nonpolar in terms of the reagents. Crown ethers. Metal atoms with full or partial positive charge are stabilized by ether solvents. Ethers are used as solvents for Grignard reactions because they can stabilize the magnesium atom. For example, here we have magnesium. Magnesium undergoes a Grignard reagent reaction with an alkyl halide, and the magnesium ion is stabilized not just by R and by X, but also by the O's of the ether. Crown ethers have been shown to form especially strong attractions to metal atoms. In terms of crown ethers, there's different types. For example, here we're seeing 12 crown 4, 15 crown 5, and 18 crown 6. The multiple ether groups result in a stronger metal attraction. The numbers in their names refer to the total number of atoms, for example, the 12, the 15, and the 18, and the number of oxygens, 4, 5, and 6. Crown ethers trap metal ions within the actual ether ring. The size of the metal must match the size of the crown to form a strong attraction. Usually, metal ions are not soluble in low polarity solvents. The crown ether complexes to the metal cation, and the resulting complex is then soluble. For example, 18 crown 6 is the ideal size to trap potassium cation. Crown ethers then are used to help ionic salts, needed often for organic reactions, to dissolve in organic solvents. Solubility of ions in the presence of crown ethers. Consider Kf. Without the crown ether, the solubility of Kf, because it is an ionic compound, in benzene is minuscule. It doesn't dissolve. However, the F- ion is ready to react because the potassium ion is hosted by the 18 crown 6. Potassium ion is trapped within the crown ether, and F- is free to then undergo reactions as needed. Choosing a crown ether depends on the metal cation present in a reaction. For example, 12 crown 4 solvates lithium, 15 crown 5 solvates sodium ion, 18 crown 6 solvates potassium ion. 2. Nomenclature of ethers and epoxides. Common names are often used for ether. 1. Name each R group. 2. Arrange them alphabetically. And 3. End the word with ether. For example, this one, ethyl methyl ether. The second ether, tert-butyl methyl ether. IUPAC systematic names. The larger R group is the parent chain. The smaller R group is the alkoxy substituent. For example, this one would be called ethoxypentane. The 5-carbon chain is a parent chain, and then this with 2 carbon is the ethoxy species. Nomenclature of cyclic ethers. For cyclic ethers, the size of the ring determines the parent chain name of the molecule. For example, oxirane ring system for 3, oxetane ring system for 4, oxolane ring system for 5, and oxane ring system for 6. Oxiranes are also known as epoxides. An epoxide can have up to 4 different R groups. For example, the carbon here and the carbon here can each have 2 different groups attached to each one, meaning up to 4 different R groups. The simplest oxirane is known as ethylene oxide, or the simplest epoxide. We can also have a substituted oxirane or an epoxide as well. Although they are unstable, epoxides are commonly found in nature. For example, in pheromones. Epoxides. There are 2 methods for naming epoxides. 1. The oxygen is treated as a side group, and the numbers are given as its locants. For example, 2, 3, between carbons 2 and 3, we have that epoxy group, then 3 ethyl for this branch, 2 methyl for this branch, pentane. The longest chain is 5. Or 2, we use oxirane as a parent chain name. The same species can also be called 2,2-diethyl-3,3-dimethyl oxirane. 3. Synthesis of ethers and epoxides. Industrially, diethyl ether is prepared by the acid-catalyzed dehydration of ethanol. Simple symmetrical ethers can be prepared this way. The first step in the mechanism is a proton transfer onto the alcohol, followed by an SN2 attack, then proton transfer, and finally release of the diethyl ether in this case. Williamson ether synthesis. The Williamson ether synthesis is a viable approach for many asymmetrical ethers. Since this reaction is an SN2 substitution, it only works well with unhindered primary and methyl alkyl halides. An alcohol first undergoes a reaction with sodium hydride, followed by SN2 with an alkyl halide. This will result in an asymmetric ether. The first step is the proton transfer. In this case, the alcohol is providing the proton, the hydride is acting as the base. The alkoxide then can attack, backside attack, on the alkyl halide, resulting in the unsymmetric ether. Example ether synthesis. Consider the 2 possible routes to synthesize methyl D-butyl ether via Williamson ether synthesis. We may either begin with the tert-butanol or methanol in order to get MTBE. The first route will work because it requires a methyl halide. How about the second route? The second route will not work as it requires a tertiary halide. So this method here will not work. Another ether synthesis method. Recall that oxymercuration, demercuration can be used to synthesize alcohols from alkenes. It is Markovnikov regional selectivity. Similarly, alkoxymercuration, demercuration can be used itself to synthesize ethers. Again, it would be Markovnikov in terms of its regional selectivity. So instead of having water, if we have an alcohol present, we'll have the formation of an ether. Preparation of epoxides. Recall that epoxides can be formed when an alkene is treated with a peroxy acid. MCPBA and peroxyacetic acid are commonly used. Here is peroxyacetic acid and metachloroperoxybenzoic acid. Epoxidation of an alkene is stereospecific. If we start off with a trans alkene, we'll get a trans epoxide. If we have cis, we'll get a cis epoxide as well, if we began with the cis alkene. Preparation from halohydrins. Epoxides can also be synthesized from halohydrins. Recall halohydrins are synthesized from an alkene. Note that in either route, from alkene to epoxide, it is stereospecific. If we have a cis alkene and we use MCPBA, or we use bromine and water to make our halohydrin followed by workup with sodium hydroxide, starting off with the cis alkene, that will result with the cis epoxide. Epoxide enantiomers. The epoxidation methods we have discussed so far are not enantioselective. So if we have chiral centers, we will end up with racemic mixtures if we have a stereoisomer that forms. Epoxidation of an achiral alkene produces a racemic mixture. The epoxidation forms a racemic mixture because the alkene can react from either face. It can have the reaction take place from either side of the alkene pi bond plane. To selectively react with one face of the alkene, a chiral catalyst will have to be used. Sharpless epoxidation. The sharpless catalyst is a chiral complex of titanium tetraisoproxide and diethyl tartrate, as you see here in the images. This catalyst will cause an enantioselective epoxidation of an allylic alcohol. An enantiomer of the catalyst, DET, will favor the formation of a given enantiomer of the epoxide. So here we have the trans 2-hexene 1-ol, an allylic position for the alcohol. If we use the positive DET, we'll get one enantiomer in excess. If we use a negative DET, we'll get the other enantiomer 98% in excess. 4. Reactions of ethers and epoxides. Ethers can undergo acid-promoted cleavage in steps. Acidic cleavage of ethers to produce an alkyl halide works with HBr and HI. If the R group is tertiary, then cleavage occurs via SN1 mechanism. Let's consider an example here. Here we have an ether. The ether will first have a proton transfer take place. Once it's protonated and the oxonium ion forms, then we can have a backside attack via SN2. A halide ion functions as a nucleophile and attacks the oxonium ion, ejecting an alcohol as a leaving group. Formation of a second alkyl halide. Here we have again, the alcohol is protonated, generating the oxonium ion. The halide ion functions as a nucleophile and via SN2 attacks the oxonium ion, ejecting water as a leaving group. If R group is aryl or vinyl, substitution does not occur. Ether autooxidation. Ethers undergo autooxidation. Laboratory samples of ether must frequently be tested for the presence of hydroperoxides before they are used because they are explosive. The autooxidation occurs through a free radical mechanism. It's a slow process, but it still occurs over time. Ethers in the presence of oxygen form a hydroperoxide. Epoxide ring opening. Epoxides are useful synthetic intermediates. Because of their significant ring strength, epoxides are reactive towards weak and strong nucleophiles, such as Grignard reagents, hydride reagents, alcohols, alkoxides, and more. When normally ethers are pretty unreactive and often used as solvents, that ring strength allows epoxides to be very useful intermediates. Regioselectivity and stereoselectivity. Regioselectivity. Epoxide ring opening is SN2, and so the least hindered carbon is the more reactive site towards a strong nucleophile. The nucleophile can attack the carbon. As it's attacking the carbon of the epoxide, there's going to be a bond breakage between the carbon and the oxygen, resulting in an alkoxide species. Proton transfer can then cause the alkoxide to become an alcohol. Stereoselectivity. As with SN2, inversion of configuration is observed. So if we have a nucleophile attacking the less sterically hindered site, we would often as well observe the inversion. If we have a chiral center, that means we're going to see that inversion. Although some groups, such as alkoxides, are typically not good leaving groups, ring opening of the epoxide is thermodynamically favored. Opening of the ring is thermodynamically favored due to the relief of ring strain. Acidic conditions. Acidic conditions can also be used to open epoxides with the weak nucleophile such as ACl, HBr, water, or an alcohol. In the first example, we see HX being used. The proton transfer occurs first. The epoxide is protonated. Then the protonated epoxide is attacked by a nucleophile in an SN2 process resulting in a product. Water can do the same and under acidic conditions, and so may an alcohol. In terms of antifreeze or ethylene glycol, this is made industrially using this method. Ethylene glycol is antifreeze that we see here. The proton transfer occurs first in acidic conditions, followed by attack by the water, and then we end up having a proton transfer resulting in the diol. Acid catalyzed mechanism. Under acidic conditions, the nucleophile attack still occurs at the less substituted carbon if a primary or secondary carbon is present. But if a tertiary carbon is present, then the nucleophile attacks there. Since the epoxide is cationic under acidic conditions, electronic effects result in the CO bond to the tertiary carbon being much weaker. If a tertiary carbon is not present, then steric effects dominate. Primary or secondary, the nucleophile attacks the less sterically hindered. Tertiary, the nucleophile attacks there due to electronic effects. We can see that we can have a partial charged carbon here with greater stability due to the R groups, so the attack will take place there. Under acidic conditions, inversion of configuration is still observed, regardless of which carbon of the epoxide is attacked. Which means if we have inversion, the mechanism is still SN2. 5. Sulfides and thiols. Sulfur appears just under oxygen on the periodic table. A thiol is an SH group, sulfur analog of an alcohol. The name of a compound with an SH group ends in thiol rather than ol. For example, if we have 3-methyl-1-butanol and we have the analogous thiol, it would be called 3-methyl-1-butane thiol. Thiols are also known as mercaptans. The mercaptal prefix is used in the name SH as a substituent. So we can either call this a thiol or mercapto. This one is called 3-mercapto, 3-methyl-1-butanol. Dimercaprol is used to treat mercury poisoning. This is dimercaprol, 2,3-dimercapto-1-propanol. Nomenclature of sulfides. Sulfur analogs of ethers are called sulfides or thiol ethers. Here is diethyl ether. Analogous to it is diethyl sulfide. Sulfides can also be named as a substituent. We can call it a methyl thiol group. Here we have a methoxy group, 1,1-dichlorophore-methoxycyclohexane, and here we have 1,1-dichlorophore-methyl-thiocyclohexane. Some properties of thiols and sulfides. Thiols are known for their unpleasant odor. Skunks use thiols as a defense mechanism. Methane thiol is added to natural gas methane so that gas leaks can be detected. Because sulfides are readily oxidized, they make good reducing agents, and we saw what DMS is used to reduce ozonide and complete the ozonolysis reaction. So we have seen this reagent before. An alkene can be converted into two carbonyl groups by the use of ozone and workup with DMS. Preparation of thiols and sulfides. Primary and secondary thiols can be synthesized from SN2 reaction of sodium hydrosulfide with an alkyl halide. The hydrosulfide ion HS- is a strong nucleophile and a weak base. It promotes SN2 rather than E2 reaction. Sulfides are generally prepared by nucleophilic attack of a thiolate on an alkyl halide. Thiolates are formed by deprotonating a thiol with sodium hydroxide. So taking a thiol, for example, that we see here, it can undergo H+ subtraction with a strong base like sodium hydroxide, forming the ion. Then the ion can attack via a backside attack or SN2 an alkyl halide, forming the sulfide. Preparation of disulfides. Thiols are oxidized to disulfides with bromine under basic conditions. A disulfide can be reduced to corresponding thiols with zinc metal. The interconversion between a thiol and a disulfide can also occur directly via a free radical mechanism. The bond association energy of a disulfide bond or SS bond is only about 53 kilocals per mole, and so the bond is easily made and broken. And the shape of proteins relies on this bond being easily broken and made. Sulfide reactions. SN2 substitution with an alkyl halide. The product is a strong alkylating reagent that can add an alkyl group to a variety of nucleophiles. Oxidized to sulfonoxides or sulfones. The choice of oxidizing agent depends on whether one needs to make a sulfoxide or a sulfone. So a sulfide can undergo oxidation to form the sulfoxide and the sulfone. Sodium periodate can also be used to form the sulfoxide. Hydrogen peroxide can be used to form a sulfone. Here is methylphenyl sulfide undergoing a reaction to form the sulfoxide. Here is another sulfide undergoing a reaction with hydrogen peroxide to form the sulfone. 6. Synthesis overview. Epoxides allow for the installing of two functional groups on adjacent atoms. Whenever you see two adjacent functional groups, you should think of an epoxide made from an alkene as the starting material. So here's our alkene, and eventually, if we can turn this into an epoxide, we can get two different functional groups on adjacent carbons. Synthesis, carbon skeleton modification. By reacting an epoxide with the Grignard reagent, the carbon skeleton can be modified. Think of the alkyl halide as a starting material to which carbons will be added via Grignard reagent. The epoxide consists of the carbon chain that will be added to the alkyl halide. The epoxide yields a longer carbon chain with a functional group on the second carbon of the newly installed chain. For example, consider the reagents necessary to accomplish the synthesis of taking a bromobenzene to this product here. Well, we need to add a 3-carbon chain with the functional group on the second carbon of the new chain. We know an epoxide should be used. We're going to use magnesium and ether to generate the Grignard reagent with our starting substrate. Then we will use the appropriate epoxide, followed by the workup with water and